All right, so I'm going to talk about this Thor-Soar agent that's been being developed in the environment they just presented. The goals for the agent are to create a reference embodied SOAR agent, meaning something that we can share with others to show, and also it's been a research project to determine how to best do environmental interactions, also how to represent things that we normally represent in goals, but in a more complex environment than possibly we've done before, including goals, how the world is represented, how we represent objects and relations. Also, we're going with we're still using SOAR operators, but we're expanding the kinds of things we're doing with them. And also how to use different general problem solving and planning capabilities. And then how to ground specifications that are gotten from interaction with humans and have a consistent way of doing this. This then is to support language integration. So what is the target representation for language when we're parsing language, what it should produce, and also for interactive task learning is what knowledge needs to be learned. So we're really defining the different kinds of knowledge we want to learn for interactive task learning. In designing the agent, we're trying to have a flexible goal and task specification and have minimal task preparation so we don't have to train the system. And I must say that within this environment, RL is really a non-starter, giving the space of goals and objects and things like that we want to learn. We want to have efficient problem solving, and just brute forward search is also a non-starter. If we look at the branching factor, it's 70 objects out there with 3 or 4 actions per object. That gives you the branching factor at each step. Forward search isn't going to do it. We want to be fast execution, faster than real time, and support multiple levels of knowledge. We want to have agents that are not know a lot about the world and have to do a lot of planning, for example, and also ones that can go very fast. So the environment we're working in, at least to start off testing, is a kitchen environment with over 75 objects. These are 75 objects existing in the world right now. And then there's about 14 or 15 physical actions we can apply. They don't apply to all things. Some of them are kind of fun actions like slice, which destroys the original object and creates like 6 new slices of potato, and that just makes planning a lot of fun. So just to give you an example, here's going to be a trace of the system solving the problem where we tell it we want the bread to be toasted. We're not going to tell it how to do that. And it turns out you can only put, guess what, you can't put a loaf of bread in the toaster. And then we say the toasted slice should be on a plate and the place is on the counter. So I just hit go and that is off and running. So it figures out it has to slice it first, takes a slice, heats it in the toaster, goes, gets a plate, puts the plate down, go get the toast and puts it on. And by the way, it has 1 arm, so it can't do 2 things at once. So what's our world representation conventions? So we have the eyeball bringing in sensory information. Then we have what we call the scene, which is where we're maintaining all the objects. This is a symbolic scene. There's SVS on the other side. I'm just not going to chat about that very much. So there's going to be the things it can perceive right now. There's going to be things it perceived in the past that it can't perceive right now. And then there's going to be things that recalled or hypothesized should be there based on somatic or episodic memory. From then we attend to a subset of that because this is 70 objects, possibly. So we attend to those that are relevant to the current goals and actions it's trying to perform. And that's done by looking at what those are. And then we do reasoning over that set. Right now, we do the agent decision-making and planning. The agent is about 800 rules, which is like 3 times as big as I ever thought it was going to be. This is without the natural language components we'll hear about later. So we use means-ends analysis, which was originally developed in 1959. It was then also used in a system called Prodigy 32 years later. We're 34 years after that. Don't ask me when SOAR was created. So the idea and means-ends analysis will go through in gory detail, but the general idea is it can take general problem-solving knowledge so that you can really be efficient. And the kind of knowledge is it's better to try to get an object in position before you try to get the robot in its final location. Because you can always move the robot, but you can't always move objects. We use look-ahead search via iterative deepening, and we'll go through that. And then we convert that search into control knowledge via chunking. And so here's an example. We're going to move the potato into the fridge and close the door. It's just simple so we can walk through it. The actions it will perform are open the fridge, approach the potato, pick up the potato, approach the fridge, pick up, put it in the fridge, and then close it. you'll notice I have these numbers associated with the objects. That means we're getting that exact object. We're using that as simplification at this point in the talk, so we don't have to refer to grounding issues. So here it just did it. So it's going off doing it, it opened it up, it then picks up the potato and it puts it in the potato and closes it. Boom. That's actually slower than real time. That's with the debugger running. We can run faster than that if we have to. Okay, so here's means ends analysis. The basic idea of means ends analysis, you look at your goal and you say, what's my goal? I'm going to select an action that helps me achieve my goal. And then I'm going to figure out how to get that action so that I can achieve that. So to start off, our goal is the potatoes in the fridge and the fridge is closed. We then know that from general knowledge that we should try to do in relations before we try to do closed relations. That's just general knowledge the system has. We then look at our operators and we find an operator that will achieve in that, and it's called the put operator. So we select that. We actually select it even though the preconditions aren't satisfied, and this is what's called operator subgoaling for means ends analysis. So we select it. We then look at what are all the preconditions, and this is represented in the operator when it's proposed. And it says I have to have the object I want to put things into open. I have to be holding an object, and then that object that I want to put it into has to be reachable. Turns out right now the refrigerator is reachable, so that's in italics. And this ordering of coloring tells us the ordering we have to go through. We should go through in trying to achieve these sub goals. So the first thing we should do is try to open it. And so we then say open the container. We then say what do we need to do to open a container? Well, we have to be holding none, which we aren't. We have to be reachable. It turns out we're right in front of the refrigerator, which is great. And the refrigerator has to be off. What that really means is we can't open the microwave when it's on. So any object that has an on or off thing like that, it has to be off. So we open it, boom, it's open. We apply it, we open it. And now we go to the next sub goal, which is holding the object. So we try to do, so we look around, we find out the operator that can do that is get object. We then decompose that into its subset, sub desires, and one of them is holding none, which is already achieved, but it's not reachable. And accessible means that it's in a place that isn't like a closed object, like it can't be in the microwave with the door closed. So accessible is another thing. So it says, let's go reachable. Let's do that. Are we mobile? Meaning we're not stuck somewhere. And then we go and apply it. And now we approach the potato. Woo! Okay, we're now reachable. We now can apply this, which is actually do the physical object. And we get the object. So now we've got the potato. Boom, this all goes away. And we had to change this because anyway. So, but now we're not reachable anymore. Remember, because we used to be reachable, but we moved. And so that goal now becomes undone. And so we're trying to do that. We go approach the refrigerator. And now we're reachable. Now we apply. So now we apply put in. And we put it in. And then we apply close. So now you've seen how we do means ends analysis. Okay. And this is the kind of. There's actually more stuff in here, but this gives you the general sub-goal hierarchy you would see in SOAR by doing this task. All right, well, that works great when you've got these tasks that everything you know how to do. But what happens when there's uncertainty, where there's multiple, and so you need, when the search control is insufficient, you must search because you might have concurrent goals. I have two things I need to achieve, and I don't really know which one I should do first. There's multiple actions that can achieve a goal, or there's multiple objects that can achieve a goal, so I have to search. So we use iterative deepening, and I'm not going to slow down. Okay, iterative deepening means iteratively increasing the depth of a depth-bounded depth-first search. So it looks like breadth-first search, but you do one depth, you do two depths. Oh, you don't even have to imagine it. I'm going to show you. And it is compatible with means ends analysis. So iterative deepening is first, you go one depth, one depth, one depth. Then you go two depth. Then two depth. This was so much fun. And then two depths. And then you go, and this is where I got tired. Three depths. Okay. So for make coffee, so say we want to do two things. We want to do make coffee and we want to cook the potato. And we're not saying which one you do first. Turns out cooking the potato takes longer than making the coffee. And we want to minimize time. So what? Go start cooking the potato and then we should go make the coffee. It turns out the solution is at least 11 steps of actions. And it turns out if we do it this way, it takes 681 decisions because we're going one depth, two depth, three depth. But the only choice is which one to do it first, because once we decide to make coffee, we know how to make coffee. And once we know how to cook a potato, we got to cook a potato. So guess what? We are doing a new kind of algorithm, iterative deepening impasses. So we iteratively deepen based on when we hit impasses. So this is a conceptual idea of it. It's not how it actually shows when I show it. So we start here, we do this. It turns out there's only one option. Go do that. Keep doing that. Oh, now we've reached the goal. So this is depth 1 of impasses. Now we say, well, what's depth 1 for the next guy? The next depth 1 for this guy is go 2 steps in a row because there was no uncertainty. How about for the other guy? Well, it turns out that was 1 step because there's uncertainty after that. So now we already achieved the goal on the first side, so we don't have to do that again. So now we're coming down here, now we expand this one. Now we go over here and we expand this one. And so that is the total search tree, okay? But we've done it without having to just waste time. So it turns out if you do this kind of impasse-driven iterative deepening, it only takes 185 decisions as opposed to 681. And that's cool. And of course, Jill's going to ask me, if she's still on, what happens with chunking? With chunking, it's only 64 decisions. Now, it turns out that there's 20 or 30 decisions at the beginning where it's just getting its feet wet and figuring out the world. So that's really good, okay? And so this is what it looks like to do this task. It puts in the potato, it goes and starts it cooking, and it made the coffee. And so while it was cooking the potato, it was making coffee, and so the elapsed time was minimal. That was so cool when it happened for me the first time, but I don't know. The next problem we're going to talk about is goal specification. I want to specify a goal. So what we saw before is I know exactly the object and I say that it has to be cooked. But sometimes you have partial descriptions and you don't really know the exact object you want to have that you want to talk about. And also sometimes you want to specify conjunctions. I want to have this done and this done and this done. Or you want to have disjunctions. I want to have this done or this done and that done. So we want to have a language we can specify, and also we can provide temporal order. First do this and then do that. So that is what we've implemented, is there a system of that. But the key question is, how do we figure out which object is being referred to in the with all this information? And we'll get to that soon. And so the idea is that the parser transforms action specifications into state descriptions. So if you say, put the apple in the fridge, this is going to be translated, right, Peter and James, into the apple is in the fridge. Or if you say, make coffee in the mug, it's going to be the mug is full of coffee. This allows the agent to figure out what the best way to achieve the goal is, given its affordances. So you don't have to tell it, and it says, I can't do that, I've only got 1 arm. It will figure it out on its own. There is some issue, is that it might do things not the way you want, and so we have to figure out how to do that. You know, if you have certain preferences that you have to have it done in a certain order. So what it does is it attempts to ground this description to an existing specific object in the world, and we have this idea of a unique object handle, which specifies that object in the world. So there's a unique identifier for it. So if we want to have the fridge closed, it would say, we have an object, that object is the fridge 30, and it's closed. Open fault. So that's what we do. But there's fun with grounding. Right, Peter? If you want to use properties and relations to designate an object. You don't really know that it's fridge 14, or you don't know that it's apple 14. You want it to be the green apple on the nearby counter. Should be cooked. Or the object is not even currently sensed. You don't even know that there's an object there. You're only going to find out when you open the fridge that you find out that there's an apple in the fridge, and that should be cooked. So you don't even know it when you get it. Or the original object is transformed to new objects with new affordances. So it turns out when you have an egg, you can't cook the egg. But if you break the egg, you can cook the broken egg, well, the egg that you get out of it. And the egg that you get after you break it is different than the egg than you started with. Fun. And also, sometimes you want to do an action internally, like you say, I want you to slice the piece of bread. And so it says, okay, I want to slice a piece of bread. and then it says, oh, I've got to find a knife. You didn't say anything about knives. It's got to go out and find a knife on its own. So all of this makes it more complicated to ground. So our general approach to grounding is when we can't find something immediately, we create an ungrounded description of the object. This is what Aaron did in his thesis. We create a unique hypothetical object handle. So we're going to have a referent to it that's hypothetical. And then we're going to include the hypothetical handle in a goal description. So if we want to hold the apple in the refrigerator, we're going to have the description of this goal is that in something in the fridge, there's this thing that's the apple. And I actually get to show Soar representation. And so we're going to say that argument 1 is ungrounded and it has object handle this. Oh, it would also say that it's of category apple. Forgot to say that. So it's going to know that it's category apple. And this, well, we've already grounded it and we figured it out this. So this is going to be the description that we work with. We're also going to so this is something we know about in the world. And then our final description of the desired is actually that we're holding object X apple 2, 3, 4. It's just a thing that that's what we want to have. So the way we're going to work this is that we get this description. What are we using? Means ends analysis. We want to have an operator that is going to help us achieve finding the fact that that apple is there. So we have this operator called find object that looks for ungrounded objects in the goal structure. And then what it does is it's precondition, meaning it's going to set up subgoals that we want a subgoal now to find an object that satisfies that description. And that's going to become a goal. And so we might have, and then once it applies, once we've done that, what the find object operator does is it replaces that hypothetical one we actually find. So how do we do find object? Well, find objects creates this goal that we need a description. And guess what? We're going to say there's a lot of ways you can find that description. So we have things called knowledge operators. We have an operator that searches for objects that satisfy the description in the scene. So remember, we're usually reasoning about the world, where we're going to go back and look, hey, is there anything in the scene that we've seen in the past that could do it? And so we ground to the scene object. Oh, maybe there's something in semantic memory. Maybe we should search semantic memory. Maybe there's something in SVS that we could extract out. Maybe there's something in episodic memory, and I think this has real promise. And maybe we should explore the world. Maybe we should ask the human. But the point is, we set these up as operators that we can select between. So now we have another place where we're using means ends analysis. We're using search in order to do that. All right. Right now, I've talked to you about where we have omniscient sensing, and what we're doing is we're removing that, and we're going to a system where the agent just has a viewing frustrum, and it actually, when it wakes up, it goes and spins around the world and records everything it sees and starts building up its own model of the world. So we're doing that, and then we also then find all the containers, and we go and open up all the drawers and look in the drawers to find out what's in the drawers and in the cupboards. Hopefully you're not there in the room when it's doing that. We also decided that, well, it would be nice if the system could figure out what the affordances are. So the agent will also go around to all the objects and it'll start playing with them and see what it can do with them. This is things like, can it open it? Can it grab it? Is it fillable? Can I make it dirty? Can I clean it? We've decided not so far to see if we could break it or if we can slice it or we can cook it. And those are kind of hard because slicing and cooking require other objects. So that's future work, but we hope to get this out of interacting with a human. So the goal is we've worked a lot on defining these agent conventions. I think we've got a general efficient problem solving. We've integrated means ends analysis, iterative deepening, and chunking. We still have rough edges. Some of the search control on the agent is a little bit specific, and there's sometimes some chunking issues. Surprise. And there's some grounding issues. We need to exploit episodic knowledge, and we still and we need to create a domain independent version of the code so that somebody not using Thor-Soar can use all the conventions and stuff we've developed for their own new task. I have ported this to the blocks group just to test out Sussman anomaly, and we do have Sussman's anomaly, so that's something to work with. All right, so here's your moment of Zen. This is making breakfast. Come on, baby, make breakfast. Anyway, any questions? I got about a minute. Yeah,
Thinking about forms of temporal reasoning, so don't kill the climate, keep it in the fridge open for a long time, don't have cold coffee by the time your potatoes cooked. It sort of sounded like that was implicit right now in terms of just optimizing total time.
yes, that's gonna be all implicit, yeah.
as
Now,
opposed to
I must say that it doesn't have anything that says I must keep all the cupboards closed, so that has to be an explicit goal, because maybe you're not the kind of person, you wanna leave all the cupboards open. Some people
So you can see everything.
see everything, and, yeah. So anyway, it just made coffee, made some toast and did an egg for me. All right, thank you. I have to stop because I'm over time.